Hi, this is Dr. Austin Head, and welcome back to Into the Cortex. In previous episodes, the two cognitive systems that people use to process information about the world around us were discussed. One system, System 1, is responsible for making rapid, intuitive decisions about the world. It is most effective and accurate when dealing with everyday, routine situations. The other system, System 2, is used to solve unfamiliar, abstract, logical problems. System 2 is what people use to develop accurate scientific explanations for phenomena. The focus of this particular episode is how System 1 thinking can adversely affect the development of those accurate scientific explanations. First, let's review how System 1 works. When attempting to resolve a problem or situation, System 1 searches through long-term memory. It matches attributes of the current situation to a collection of images and ideas stored in long-term memory. This is why System 1 is particularly effective at processing familiar everyday situations. It uses what the brain already knows and applies it to the current situation or problem. I can demonstrate how System 1 works using an example from a previous episode. All you have to do is read the words that appear on the screen and note that what pops up into your mind. Are you ready? Go. When you saw this unusual word pairing, it is likely that some strange images came to mind. For example, you may have imagined an animate, barfing banana or some other unusual scene. This occurs because your brain processes snippets of information from long-term memory, melds the bits of information together in order to interpret the meaning of the two words. In only a few seconds, you probably started to question your thoughts. This is because your System 2 went online and you started reflecting more deeply about the situation. Now I'll demonstrate how System 1 thinking can produce scientifically inaccurate explanations for natural phenomena. I will provide you with another example presented in a previous episode, the four seasons. Specifically, I want to address the question, why is it warm or hot during the spring and summer and cold or freezing during the fall and winter months? Science education research reveals children and adults commonly maintain the misconception that the differences in temperature between the seasons are due to changes in the distance between the Earth and the Sun. It goes something like this. During the fall and winter months, the Earth is farther away from the Sun. Subsequently, the temperatures are lower. Conversely, during the spring and summer months, the Earth is closer to the Sun and the temperatures are higher. The scientific explanation is the distance between the Earth and the Sun does not change significantly. Instead, the temperature differences are related to how the Earth is tilted on its axis. For example, in the northern hemisphere during the spring and summer months, the Earth is tilted such that the northern hemisphere receives more sunlight. This results in higher temperatures. In the fall and winter months, the Earth is tilted so less light hits the northern hemisphere, which subsequently results in lower temperatures. So why do people believe this? Well, their life experiences are that when you come closer to a hot object, you feel more intense heat, and as you move away from it, you feel cooler. A wealth of such life experiences lend themselves to explaining the seasons in this way as well. So how do humans develop such intuitive theories about the natural world? Well, first I want to start with my explanation with a demonstration. I'm about to drop this banana. All you have to do is watch what happens. Are you ready? Go. So were you surprised by what you saw? Could you not believe your eyes? If you are like most humans, you found the floating banana phenomenon to be, well, very suspicious. Almost immediately after viewing the floating banana, you began to doubt that it actually happened. Somehow you just knew that bananas don't hover in the air. So how is it that you so quickly detected the banana farce? Well, the answer is through your life experiences. Not long after we humans enter the world, we start observing what is going on all around us. Through countless observations during infancy and through early adolescence, we learn that untethered objects fall to the ground when they're dropped. Based on a multitude of such observations, the brain develops an intuitive theory of free-falling objects. We know this is what happens from developmental studies of human infants. For most children and adults, a flying banana sets off an internal alarm indicating that something's wrong. However, to a 3-month-old infant, a falling object suddenly stopping in midair is not surprising at all. This is because they have yet to internalize a theory of free-falling objects. It's only after approximately 6 months of age that human infants develop such a theory. At that point, they too are surprised when they see an object like a banana hovering in midair. In the case of free fall, our intuitive theory is correct. However, many, perhaps most of our intuitive theories about the world around us are inaccurate. I'll demonstrate this through a word problem on circular motion. A man is holding a rope that has a ball attached to the opposite end. He twirls the rope over his head so the ball is moving in a circular path. If he lets go of the rope, the ball will A, continue to move in a circular path, B, proceed along a straight path, or C, randomly move in different directions. So what is the answer? I'll give you a few moments to think this over. Well, the correct answer is B. The ball and the attached rope will move in a straight line, tangential to the point at which it was released. The intuitive and popular response among children and adults is that the ball and rope will continue moving in a circular path. Even individuals with training in physics can have this common misperception. So how does this intuitive response form in the brain? The answer, once again, is experience. Starting in infancy, humans observe innumerable tangible objects in motion. The motion of such objects is continuous in terms of the direction, as long as something or someone does not interfere with the object. Unless a person grows up on a ranch where it's a common event to lasso a cow or a horse, they will have very limited or no experiences with circular motion. Subsequently, when faced with a rather unusual phenomena of circular motion, individuals apply what they know, their intuitive theory of continuous motion. As a result, they conclude that the ball and rope will continue to exhibit looping circular motions. I'll provide you with one more example of how intuitive theories can produce erroneous conclusions. Consider this problem. What do I need to do in order to balance this meter stick on a fulcrum? Well, based on innumerable experiences interacting with objects, human children develop an intuitive theory for the center of gravity. The theory is something like this. In order to balance an object, you must place the support or fulcrum at the center of the object. The developmental psychologists Annette Karmeloff-Smith and Barbel Inhelder conducted a classic research study focusing on the development and application of children's intuitive theories for balancing objects or center of gravity. In the study, 4, 6, and 8-year-old children were given cylindrical rods and were prompted to balance the rods on a fulcrum. Well, unbeknownst to the children, the researchers placed weights in the rods. Subsequently, the rods could not be balanced by placing the middle of the rod on the fulcrum. What the research discovered was that their 4 and 8-year-old children could consistently and efficiently balance the rods on the fulcrum. However, the 6-year-olds consistently failed to balance the rod on the fulcrum. The experimental results are directly connected to the children's intuitive theories about how an object can be balanced. The 4-year-olds did not yet possess an intuitive theory and used a simple trial and error process to balance the rods. The 6-year-olds did have a well-developed intuitive theory for the center of gravity. They continually tried to balance the rods near the center. Their blind allegiance to their intuitive ideas prevented them from balancing the rods. Finally, the 8-year-old children initially applied the same intuitive theory used by the 6-year-olds. However, the 8-year-olds also possessed a more mature and developed system too. Subsequently, they were able to change their minds and take a different approach to balancing the rods. The phenomenon of circular motion and the balancing of objects or center of gravity reveals some interesting attributes about our intuitive theories. First, our intuitive theories about the world can be incompatible with the accepted scientific explanations for phenomena. This can lead to erroneous conclusions about how the world works. Second, our intuitive theories are robust and resistant to change. The intuitive theories that we humans develop during infancy and early childhood remain with us intact over our entire lifespans. The intuitive theories that people have about the world are one reason that science content can seem so strange and difficult. In the next episode, we'll start exploring ways that people can address the inherent challenges to accurate science thinking. Specifically, the episode will focus on how individuals can increase their awareness and understanding of the variables that impact science thinking and learning. This heightened sense of awareness is something I refer to as science mindfulness. Until next time, keep on sciencing.